Welcome back to the deep dive. We sift through, well, frankly, mountains of information-dense papers, cutting-edge research, sometimes even our own slightly frantic notes, all to bring you something truly transformative. And today, oh boy, today we're not just looking at an interesting theory, we're really embarking on a
Yeah.
journey to understand something fundamental, something potentially universal that could genuinely reshape how you see, well, pretty much everything. Think about this for a second. What if? What if the way a simple metal ring spun just right suddenly snaps into a perfect polygon shape? Or the way a leaf grows, that intricate specific pattern, and then scale way up the huge swirling arms of a galaxy billions of light years away. What if all of that, the ring, the leaf, the galaxy, is governed by the exact same underlying principle, the same geometric law?
It sounds almost too simple, right? Too elegant, maybe.
Exactly, too unified. Could the universe, at its absolute core, not be this random chaotic dance we often imagine, but actually built on these incredibly precise, predictable geometric patterns, woven into reality by something, well, surprisingly straightforward?
Well, that's the core of what we're digging into today.
That's our mission for this deep dive. We're calling it the time fraction spiral law. And I have to say, the more we've researched this, the more it feels like this is huge. This isn't just an interesting concept. It feels like a potential game changer.
It really does. It's a new lens,
Yeah.
genuinely, for understanding the world. From the quantum scale, like unbelievably small,
All the way up to the cosmic web, the largest structures we know.
and right down into the cells that make us up. It connects everything. We're going to try and unpack how these really simple phase fractions seem to dictate the most complex structures we see.
Like a hidden blueprint.
Exactly. A hidden blueprint for almost everything. And honestly, the claim here isn't just descriptive, it's predictive. It provides clear, verifiable, and this is critical, falsifiable predictions.
That's the key for actual science, isn't it? You have to be able to be proven wrong.
Precisely. So we'll meticulously explore what a phase field actually means. No mysticism, no hand-waving, just physics. We'll look at why specific time fractions, numbers like
Yeah.
12, 13, 15, seem to act as these universal instructions for geometry.
And the spiral. Why does the spiral keep showing up everywhere?
Ah, yes. We'll explore why the spiral emerges as this kind of ultimate shape of maybe compromise, or flow, the fundamental attractor state for so many systems.
And this isn't just abstract physics, right? This has real-world relevance.
Absolutely. This is about understanding the hidden mechanics behind life itself, behind the cosmos, and maybe even figuring out how we could engineer solutions to some really big human challenges. Prepare for some genuine aha moments. I truly believe you'll never look at a flower or a storm or even the patterns inside your own cells the same way again after this.
All right, let's dive in. Fundamentals first. What is a phase field? And phase itself, let's be crystal clear, we're talking mechanics here, not metaphysics.
Exactly. Strip away any mystical connotations. Think about any process that repeats itself, anything cyclical.
Like a wave going up and down, a sine wave.
Perfect example. Or a blinking light, an LED maybe, on, off. Steady rhythm.
Or even biological things, like heartbeats.
Or the electrical signals that pulse across a sheet of living cells. All of these are repeating cycles, and phase is simply, well, where something is in its cycle at any given moment.
Okay, so like on a clock face. 0 degrees is the start, 180 is halfway, 360 brings you back around.
Precisely. It's just an angle, 0 to 360 degrees, indicating its position in one full rotation, one full cycle. A single blinking light, a single oscillator, has one phase number at any instant. Easy enough.
But things get interesting when you have many oscillators
Right.
spread out in space.
That's exactly where the phase field comes in. If
Yeah.
you have lots of these little cyclical processes happening across an area or a volume, think of that sheet of cells again.
Okay.
A phase field, mathematically, we write it as theta x, y, t, is basically a map. For every location, every point x, y in your sample at a specific time, tt, this map tells you the phase, the angle of the cycle happening right there.
So it's like assigning a tiny clock hand to every single spot, all ticking along, but maybe slightly out of sync with their neighbors. A map of local time.
That's a fantastic analogy. A map of what time it is on the local cycle. Everywhere, simultaneously. And this isn't just a theoretical idea. We can measure these things.
How? How do you actually see these phase fields?
Scientists use standard techniques, things like Hilbert transforms or lock-in amplifiers. These are tools specifically designed to pull out periodic signals, even from noisy backgrounds. They let us precisely measure these phase values, whether the signal is electrical, optical, or even mechanical vibrations. We're not guessing. We're measuring the tick-tock everywhere.
Okay, so we can measure them. But the really mind-blowing part, the part that makes this potentially so powerful, is that we can control them too.
Yes, this is absolutely critical. This is what elevates it from just observation to potentially engineering reality. We can actively set these phase fields
Oh.
by using external drivers. Think about placing electrodes around a sample or using carefully aimed speakers or pattern light sources. If you drive the system with these sources, and this is the crucial bit, you precisely control the relative phases between those driving signals.
Ah, the timing difference between them.
Exactly. By controlling those relative timings, those phase differences,
Yeah.
you can actively create and sculpt the phase field within the sample.
Yeah.
You're basically telling the system how its internal clocks should relate to each other across space.
Right.
You're conducting the temporal orchestra.
Which brings us squarely to those magic numbers, 12, 13, 15. These time fractions, they aren't random, are they? There's something fundamental about them.
Not random at all. They are deeply significant, and there are two really useful ways to think about them, both purely mechanical, purely mathematical.
Okay, give me the first way.
The first way is to think about them as defining the relative angles between your driving sources. Imagine you're setting up drivers around the edge of something, like that plate experiment we'll get to.
Okay.
So 12 means you have two sources, maybe two electrodes positioned exactly opposite each other, 180 degrees apart. Their signals are perfectly out of phase. This sets up the simplest possible difference, a polarity, a this way or that way.
Like a north and south pole.
Precisely. Now 13 means three sources, spaced equally at 120 degrees apart. Think of an equilateral triangle. This setup is fundamental for what's called triad closure or hexagonal closure. Three equal forces at 120 degrees perfectly balance out. It's inherently stable.
And 15.
Five sources spaced 72 degrees apart, a pentagonal arrangement. This specific angle relationship, as we'll see, leads to pentagonal symmetry, or more profoundly, structures related to the golden ratio like quasicrystals or spirals. These are literally the setup instructions for your drivers.
Okay, that's one way of the physical arrangement and relative timing of drivers. What's the second way to interpret these fractions?
The second way is to think about the phase step per tick if you're advancing something sequentially over time. Imagine you're stepping through phases.
Right.
A 12-cycle step means each tick jumps the phase by 180 degrees. It's like flipping a switch back and forth between two opposite states, on, off, plus, minus.
A binary toggle.
Exactly. A 13-cycle step means each tick rotates the phase by 120 degrees. This cycles the system through three distinct states in a repeating pattern. 1, 2, 3, 1, 2, 3.
Yeah.
Very balanced.
Okay.
And the 15-cycle step, that's a 72-degree rotation per tick. Moving through 5 states with a specific angle is where things get really complex and interesting. It's where you start seeing these non-repeating but highly ordered patterns emerge, the spirals, the quasicrystals. It doesn't settle into a simple loop like the 13th step.
So the absolute crucial thing here, just to hammer it home, is that these fractions, 12, 13, 15, are not fuzzy concepts. They are precise mechanical mathematical definitions. They describe how you set angles between sources or how you step phase over time. No woo-woo involved.
Zero woo-woo. Just precise control over cycles. It's engineering with time, essentially.
Okay, that sets the stage beautifully. We understand phase fields, and these critical fractions. Now, the giant leap. How do these abstract angles, these timing relationships, actually create tangible shapes? Why do these fractions matter for geometry? This feels like the core of it all.
This is the core mechanism. This is where the abstract math meets physical reality, and it is genuinely stunning to witness. Let's go back to that simple setup. A thin sheet or plate.
Okay.
We drive it with n waves. They all have the same energy, the same frequency. They're spaced equally around the rim, but, and this is everything, we control their relative phases using those fractions we just talked about.
So same energy, same frequency, just changing the relative timing between the drivers.
Exactly. Mathematically, you're just adding up cosine waves, but each wave has its own phase offset, phi, determined by our chosen fraction. That's the only difference between the experiments.
Okay, so what happens when n2, the 12th fraction, 180 degrees apart?
The system spontaneously locks into simple straight stripes. We call them polarity rails. It's that basic this way or that way orientation emerging directly from the 180-degree phase difference. The simplest possible pattern.
Makes sense. What about n3, the 13th fraction, 120 degrees apart? This is where it gets more structured, right?
Oh, yes. This is where you see one of nature's favorite patterns emerge spontaneously. Those three waves, 120 degrees apart, interact in a way that locks the system into a perfect, stable, hexagonal lattice.
Hexagons. Like honeycombs.
Exactly like honeycombs, or the way soap bubbles pack, or as you mentioned, epithelial cells. It's the geometry of maximum stability and efficient packing. Why? Because three equal vectors at 120 degrees sum to zero. It's a perfect force balance, a closure condition. The system finds this incredibly stable, low-energy state.
Wow. Okay, and then N5, the 15 fractions 72 degrees apart. This is the odd one out, geometrically speaking.
It is, and that's its power. Five-fold symmetry, unlike hexagons or squares, has this inherent problem. You cannot tile a flat plane perfectly with pentagons. You'll always have gaps or overlaps. It's geometrically frustrated. But that frustration isn't a bug. It's a feature. It forces the system to find a different kind of order. Instead of a simple repeating lattice, it settles into these beautiful, complex, non-periodic patterns like decagons or quasicrystals. And crucially, if you add just a tiny bit of slow rotation or a slight energy gradient,
Spirals.
logarithmic spirals emerge. It's the system's elegant way of resolving that geometric impossibility, allowing for continuous growth or flow without perfect periodicity.
So the truly profound insight here, let me see if I've got this. You keep the total energy the same.
Constant.
Keep the frequency the same.
Constant.
Keep the material the same.
Constant.
And you change only the relative phases between the driving points using these 12, 13, 15 recipes.
Precisely.
And the entire geometry of the pattern fundamentally switches from stripes to hexagons to decagons or spirals.
Instantly.
Yeah.
Deterministically. It's like flipping a switch for shape using only time. It's genuinely reality bending when you see it.
I believe it. Can we actually see this? Are there simple ways to demonstrate this visually?
Absolutely. There are several straightforward experimental setups, or rigs, that prove this principle beyond any doubt. Let's talk about three quick ones.
Okay, first up, the plate and powder rig. This sounds like the most direct visual proof.
It really is. It's a modern take on the old Chladni plate experiments, but with much finer control. Take a simple metal plate, attach maybe 3 to 5 small, precise shakers, exciters around the rim.
Got it.
Then dust it lightly with a fine powder, like lycopodium powder, which is very light. Now, you apply your phase programs 12, 13, 15, making absolutely sure the total power going into the plate remains constant.
So run the 12 program, 2 exciters, 180 degrees out of phase. What do we see?
The power instantly collects along straight lines, those polarity rails. A clear stripe pattern emerges. Simple?
Then switch. Same power, but now the 13 program, 3 exciters, 120 degrees apart.
Instantly, the stripes vanish, and the powder rearranges itself into a stunningly clear, stable hexagonal grid. It just snaps into place. It's quite dramatic.
Wow. And finally, the 15 program, 5 exciters, 72 degrees apart.
The hexagons dissolve, and you see intricate decagonal patterns form in the powder. Or, with a slight tweak, like a tiny rotational bias in the phasing, you'll even see the powder organizing into clear spirals.
The incredible thing is the switching itself.
It's astonishing. The node lines where the powder gathers switch geometry completely just by changing the phase program. And here's another kicker. If you slowly advance all the phases together by the same small amount,
The whole pattern rotates.
the entire pattern rotates smoothly across the plate with no extra energy input. It's undeniable proof of phase-only control over spatial geometry. You're steering the pattern with time signal.
That's incredibly convincing. Okay, what about moving from powder to liquids, like water or colloids?
Good question. Same principle, different medium. Imagine a petri dish with water, or maybe water containing tiny suspended particles, colloids, that we can see.
Okay.
Surround the dish with, say, 3 or 5 electrodes, or maybe small ultrasound transducers. Put a camera overhead. Apply the same phase programs, 12, 13, 15, keeping the total energy, RMS voltage or power, constant.
What happens to the particles?
You see distinct order emerge. The 13 program will cause the particles to arrange themselves with clear hexagonal packing. You can measure this, do a Fourier transform of the image. You'll see sharp hexagonal peaks.
And the 15 program?
You'll see decagonal ordering of the particles. And often, you can induce visible spiral flow patterns within the liquid itself. The 12 program, again, creates clear lanes or bands. It shows the phase field directly organizing physical matter in a fluid.
This is all building towards something even more profound, isn't it? What about life? Can this principle actually shape living systems? This is where it potentially becomes revolutionary.
This is where the implications become,
Yeah.
well, truly enormous. This is the most exciting frontier. Imagine taking a sheet of living cells. MDCK cells are a common type used in labs. They form sheets like the lining of organs.
Okay, a living tissue layer.
Grow them on a special conductive gel. Now, place maybe 3 electrodes around the edge, or perhaps a tiny one in the middle. This lets us apply gentle, precise bioelectric fields across the living cells.
And you apply the same phase programs, 12, 13, 15, but crucially, at equal power.
Equal power is paramount. We're not zapping the cells with more energy, we're just changing the timing, the phase relationships of the gentle fields.
What are the predicted outcomes? How would the living cells respond?
The predictions are incredibly specific and quite startling. The 12 program, inducing polarity, should create axis rails. It should make the cells align, establishing a clear direction across the sheet.
Like front and back.
Exactly. The 13 program, the hexagonal closure condition, should drive compartment closure. It should encourage the cells to pack tightly and efficiently into that stable hexagonal arrangement, which is vital for healthy tissue function.
And the 15 program, the spiral trigger.
This is predicted to trigger spiral outgrowth or maybe a duplication bias. You might see cells migrating or dividing in distinct spiral patterns, or perhaps an increased rate of proliferation focused in certain ways. You'd be literally sculpting the behavior and arrangement of living tissue using only phase information.
This experiment sounds like the ultimate test. It's a direct falsifier for the whole idea in biology.
Absolutely. This is where the rubber meets the road. If this entire framework is wrong for biology, if only the amount of energy matters, and changing the phase does nothing, then running these different phase programs at the same power level should produce no difference in cell morphology or behavior.
The theory would be dead in the water for biology.
Exactly. But if we can reproducibly, demonstrably switch the collective behavior and structure of these living cells from aligned polarity to hexagonal packing to spiral outgrowth purely by changing the phase program while keeping the energy constant,
Then it's a monumental confirmation.
it would be profound. It would mean phase fields are a fundamental control layer in morphogenesis, in how life shapes itself. It would measure things like cell shape, alignment, the hexagonal order, maybe even the internal cytoskeleton structure. If phase toggles these outcomes, we've found a new way to speak the language of biological form.
So phase field stops being an abstract concept and becomes actual knobs we can turn, controls we can use to influence geometry.
That's the essence of it. When you fix everything else, power, frequency, temperature, the material, the cells, you're left with 3 main control knobs. 1, the geometry of your source is how many drivers? 2, 3, or 5.
Okay.
2, the relative phases you set between them, the precise 12, 13, 15 angles. This is the core instruction.
Right.
And 3, potentially, a very subtle, slow filter or bias in the environment. A tiny anisotropy in the substrate, maybe a slight triangular preference to help the 13 mode lock in, or a golden angle bias for the 15. Just a gentle nudge to help the system choose.
And the ultimate test is simple. Does the geometry toggle when you only change the phases?
That's it. If yes, you've just engineered shape using a phase field. If no, the idea needs revision or rejection. It's that rigorous, that mechanical, and potentially that powerful. We're talking about geometry becoming a direct output of time signals.
This is really shifting my perspective. Let's dig into the why. Why these specific numbers, 2, 3, 5? Why do they seem to be the universe's preferred language for structure? Is there some deep mathematical reason?
There absolutely is. It's not arbitrary. It boils down to fundamental symmetry mathematics, the most basic ways energy and matter can organize stably. Let's take 2, the basis for the 12 fraction.
Polarity.
Exactly. 2 states or opposite phases are the absolute minimum requirement for polarity. Up, down, left, right, inside out. It's the most basic distinction possible.
Right.
Without twofold symmetry, you can't even define an axis or direction. Think of a magnet's poles or an organism's head and tail. It's fundamental differentiation.
Okay, and 3, the 13 fraction leading to hexagons.
3 is incredibly important because it represents the first way to achieve a truly closed, stable system with equal forces. Remember those 3 vectors at 120 degrees summing to 0.
Right, the perfect balance.
That closure condition leads directly to the stability and efficiency of hexagonal packing. Beehives, graphite, bubble rafts, epithelial tissues. It's nature's go-to for strength and covering a surface efficiently. It's the universe finding a point of equilibrium.
And then 5, the 15 fraction, the misfit that leads to spirals and quasicrystals.
This one's fascinating because its power comes from not fitting perfectly. As we said, fivefold symmetry can't tile a flat plane without gaps or overlaps. That inherent geometric frustration.
Forces a different kind of order.
Precisely. It forces the system into those beautiful, self-similar logarithmic spirals, or into complex, non-repeating but highly ordered quasicrystalline patterns. It's the geometry of growth, adaptation, and resolving tension when perfect periodicity isn't possible. It's dynamic stability.
So what about other numbers we see, like 4, 6, squares, or hexagons?
They're definitely important, but often they can be seen as related to the fundamental ones.
Hmm.
Fourfold symmetry can often be seen as a doubling of twofold polarity, like two axes. And sixfold symmetry, the hexagon, is inherently linked to the stability of the threefold triad condition. It's essentially two interlaced triangles. But the core building blocks, the prime movers of geometry, seem to be 2, 3, and 5. It's the minimal symmetry math, and again, you can prove it yourself with that powder on a plate rig. It's physics, not philosophy.
Speaking of direct proof, that spinning ring observation I mentioned earlier, where it went from circular to a 4-star, then a hexagon, then a decagon, just by changing speed. That wasn't just my eyes playing tricks, that was this.
That was absolutely unequivocally this principle in action. What you saw is a well-documented physical phenomenon. It wasn't an illusion at all. A rotating system, as its speed increases, finds it energetically cheaper to break its perfect rotational symmetry and adopt these specific polygonal standing wave modes around its rim.
Mm.
You were literally watching phase locking create geometry in real time.
Wow, okay, so what's the physics? How does speed translate to shape?
At low speeds, the ring is just a circle, stable. As you spin it faster, that simple circular state becomes unstable. The system wants to find a lower energy state, and it does that by forming standing waves, tiny synchronized pulsations around the rim.
Like ripples on a pond, but on the ring's edge?
Sort of, yes. And these wave patterns are described by specific mathematical functions. Bessel functions, or Fourier modes on a circle. Mode M4 gives a 4-lobed shape, your 4-star. Mode M6 gives a 6-lobed shape, the hexagon. Mode M10 gives a 10-lobed shape, the decagon. Higher speeds provide the energy to excite these higher-order modes.
Okay, but why do they look stable, almost frozen, even though the ring was spinning?
That's the magic of phase locking. At specific resonant speeds, the speed at which the wave pattern itself rotates around the ring perfectly matches the physical rotation speed of the ring's material.
Ah, they lock together in sync.
Exactly. From your perspective, the pattern appears stationary because its rotation is perfectly canceled out by the ring's rotation. OMA, as physicists would write it. The underlying waves are real, they're measurable. It's not just visual.
So my simple observation was actually a direct demonstration of the whole principle.
It was a perfect, intuitive demonstration. The ring's physical rotation provided the time cycle. At specific fractions of that cycle, the resonant frequencies, standing phase modes locked in, producing distinct geometries, 4, 6, 10 lobes, related to 12, 13, 15 fractions. The shapes emerged directly from the physics of oscillation and phase locking. Time phasing is geometry. You saw it happen.
That's incredible. And this idea that phase becomes geometry, it scales everywhere, from the quantum world up to the cosmos. This weirdness we see is just phase locks.
That's the core argument. What we often label complexity or emergence or even weirdness across different fields might just be different manifestations of this same fundamental principle, phase fields locking into geometric forms.
Take a leaf, for example. Its shape isn't just DNA, right?
Right. DNA provides the basic instructions and materials, but the final intricate shape, the veins, lobes, edges, emerges from the interplay of various fields across the developing leaf surface. Bioelectric fields, chemical gradients, maybe even photonic or mechanical stress fields, where these oscillating fields achieve stable phase locks, dictated by those 12, 13, 15 fractions, growth is guided and stabilized. That's why all oak leaves share an oakness, the attractor shape, but each one is unique in its details, the specific path taken during development.
And quantum mechanics. Can this framework offer insights into things like superposition or collapse? That feels like a huge leap.
It's speculative, of course, but it offers a potentially less weird interpretation. Think of superposition, the particle existing in multiple states, as a smooth, undifferentiated phase state, like the spinning ring before it formed a polygon. And collapse, the moment it becomes definite upon measurement, could be seen as a boundary condition forcing a phase lock. The system is forced to choose a definite geometric state, like particle position.
What about electron orbitals, those specific SPD shapes?
Those could be interpreted as the stable polygonal modes, or standing wave patterns of the electron's wave function within the atom's potential field. They are specific geometric solutions dictated by phase relationships and boundary conditions. It potentially reframes quantum weirdness as phase geometry.
That's scaling up to planets and galaxies.
The examples become almost overwhelming once you start looking through this lens. Saturn's hexagon, a giant polygonal phase mode in rotating fluid. Spiral galaxies. Clearly, a fraction phase locks in rotating plasma and stars.
Yeah.
DNA itself. A helical spiral attractor, optimizing packing and stability through golden ratio-related pitch. Even river meanders, tracing spiral paths as water finds the path of least resistance. And Chladni patterns. Direct visualization of sound phase, creating geometry.
So the message is echoing across all scales.
It really seems to be. Everywhere we look, energy flowing under constraints seems to resolve itself by locking into specific geometries, dictated by these fundamental phase fractions. It's a universal language the universe uses to structure itself.
Given this universality and the appearance of these different geometries, is there one that seems dominant? You mentioned the spiral seems to be everywhere. Is it the ultimate attractor?
It certainly seems to be the most prevalent and perhaps the most fundamental dynamic attractor, especially when systems are under stress, growing, or flowing. The logarithmic spiral has this unique property of perfect self-similarity.
Meaning it looks the same at all scales. Zoom in or out, it's the same basic shape.
Exactly. The angle between its radius and tangent is constant. This self-similarity makes it incredibly efficient for systems that need to grow or dissipate energy across multiple scales simultaneously.
How does that work? Why is energy optimal?
Because it distributes stress or tension evenly. Imagine trying to coil a rope. A smooth spiral avoids kinks. For growth, it allows new material to be added continuously at the edge without disrupting the overall form. For dissipating energy, like in a whirlpool or a storm, it provides a smooth pathway for flow from the outside inwards or vice versa. It avoids stress concentrations.
Which is why we see it in everything from seashells and plant growth to hurricanes and galaxies.
Precisely. And even simple things, like if you drop a strand of hair, it often curls into a spiral. A dying worm collapses into a spiral. It's the default way for many systems under tension or relaxation to settle into a low-energy configuration.
But sometimes the spiral isn't obvious, right? You said it can be hidden inside other shapes.
Yes, this is a crucial point. Even when we see a polygon or a lattice, very often the underlying energy flow, the dynamic engine driving that shape, is fundamentally spiral.
Like Saturn's hexagon.
Perfect example. We see the sharp hexagonal boundary, but at its center is a powerful spiraling polar vortex. The spiral drives the polygon.
And flowers. The Fibonacci spirals we see in sunflowers or pine cones.
Those visible spirals aren't just surface decoration. They're the direct result of the underlying packing mechanism, which is driven by spiral phase waves originating from the growth center. It's the most efficient way to pack new buds or seeds, ensuring optimal spacing. The spiral is the dynamic blueprint within the apparently circular flower.
Even galaxies and the cosmic web.
Yes, galactic disks look roundish, but the active parts, the arms where stars form and energy flows, are undeniable spiral attractors. And on the largest scales, the cosmic web, while the voids might be roughly polyhedral, the filaments connecting galaxy clusters often trace out vast, subtle spiral curves. Statistically, energetically, the spiral seems to be the anchor.
So why? Why the spiral? And specifically, why does the 15 or 5 fraction seem so tightly linked to it?
It comes back to that misfit. Remember, the 15 fraction, related to pentagons and the golden ratio, cannot tile space perfectly. It creates geometric tension.
Right.
When a system is disturbed, growing, expanding, or under stress, it often defaults to this 15-related dynamic. But since it can't form a simple, closed, repeating pattern like a hexagon, the most efficient way to accommodate this misfit, to allow for continuous growth or energy flow, is to curve into a logarithmic spiral. It's the geometric escape hatch.
The universe's solution to the pentagon problem.
You could put it that way. It's the natural consequence of trying to impose five-fold symmetry constraints on growth or flow. And that fundamental principle seems to explain why we see spirals from subatomic particle tracks to flowers to storms to galaxies. It's the universal attractor born from geometric necessity.
This is vast cosmic stuff. But you said the most intimate proof might be right inside us, our own cells. How are they spiral attractor machines?
In almost every conceivable way. Look inside any living cell. Things aren't just floating randomly. Ions, water, proteins, even organelles like mitochondria, they flow, they circulate, often in vortex-like patterns.
And the structures themselves?
Look at the cytoskeleton actin filaments, microtubules they assemble into helical structures. DNA itself is the most famous double helix, a spiral staircase. These aren't arbitrary shapes. They're often the most efficient ways to pack information, generate force, or provide structural integrity.
Even mitochondria, the power plants.
Yes. Their inner membranes, the cristae, are folded into complex, often spiral-like ridges. This maximizes the surface area for the chemical reactions that produce energy. It's optimizing energy flow through geometry.
And cell division, mitosis.
The mitotic spindle, the machinery that pulls chromosomes apart, self-organizes using spiral dynamics, forming vortex-like structures to ensure accurate separation. The cell is fundamentally a dynamic, swirling spiral engine.
Wow, what about the fields around the cells?
Cell membranes aren't static walls. They maintain voltage gradients, bioelectric fields, and researchers have documented stunning spiral wave patterns in these fields propagating across tissues.
Like in heart muscle.
Exactly, and in neurons, even in simple organisms like amoebas, these spiral waves of electrical or chemical activity often act like organizing centers, like clocks, coordinating the behavior of millions of cells.
So the same 12, 13, 15 principles apply within our biology.
Directly. 12 governs basic polarity front-back of a cell, root-shoot of a plant. 13 governs the stable hexagonal packing of tissues like skin or gut lining. And 15, when cells are stressed or healing, or sometimes when things go wrong, the system often defaults to these spiral wave attractors, like those calcium spirals during wound healing.
The implications for medicine seem staggering if this is true.
Potentially revolutionary. Think about cardiac fibrillation, that chaotic heart rhythm. It is uncontrolled spiral waves in the heart tissue. What if we could gently coax the tissue back towards a stable 13 closure field instead of shocking it?
Or cancer. You mentioned tumors might be off fraction.
It's a hypothesis, but a powerful one. What if cancer is partly a disease of geometry, where cells lose their ability to sink into healthy patterns and get stuck in chaotic, perhaps spiral-like disorganized growth? Could applying a corrective 13-phase field help restore order and suppress malignancy without toxic side effects? It's a completely different way to think about treatment.
And regeneration.
We know spiral waves guide development and wound healing. Could carefully tuned phase fields accelerate or guide regeneration more effectively? Could we steer tissue repair using bioelectric signals coded with these fractions? The possibilities are immense. The cell is living proof of the spiral attractor law.
So it really boils down to a core mechanism. Disturbance hits a smooth system, it can't stay smooth. It fractures into these phase relationships, which then create geometric attractors, with the spiral being a major one.
That's a perfect summary. When smooth time or a smooth field gets perturbed or hits a boundary, it folds. It resolves the disturbance by locking into these fractional phase relationships, creating stable geometric patterns. The spiral is often the most robust and efficient pattern, especially for handling ongoing disturbance or growth.
Which explains the flower's secret Fibonacci pattern.
It has oscillating phase fields at the growth tip, creating spiral blueprints for placing new petals or seeds.
Yes. Okay, this framework is incredibly compelling, comprehensive even, but for it to be real science, it needs to be actionable, testable. You mentioned falsifiable predictions. Let's get into those. How do we actually verify this or break it?
Right. This is where we move from admiration to application, from theory to tangible results or rejection. This is where the huge potential becomes concrete. We need specific, verifiable predictions across scales.
Let's start big, the cosmos. What can we look for in existing astronomical data?
Okay, prediction A1, CMB, symmetry residue, the cosmic microwave background, the baby picture of the universe. The claim is, hidden within the standard random-looking fluctuations, there should be faint but statistically significant echoes of 13, hexagonal, and golden spiral phase patterns left over from the universe's earliest moments.
Like fossilized geometry, how would we find that?
You take the public data from satellites like Planck, use advanced math tools, steerable wavelet banks, tuned specifically for six-fold and spiral symmetries on a sphere. You calculate things like phase entropy and look for non-random correlations, the bispectrum. Compare what you find to thousands of simulated universes that don't have these patterns built in. If there's a real excess of hex or spiral signals, statistically speaking,
That's evidence.
that's strong evidence for early universe phase locking.
What about the cosmic web? The structure of galaxies? Prediction A2.
Cosmic web topology bias, the claim. The web isn't just random fluff. The vast cells or voids should show a bias towards being hexagonal, and the filaments connecting galaxy clusters should curve in ways consistent with spirals.
How to test that?
Use galaxy survey data, DXI, Euclid, SCSS. Map out the 3D structure using geometric tools, Plano-Voronoi tessellation. Then measure the shapes of the voids, count how many sides they effectively have, and analyze the curvature of the filaments. Look for that hex bias in the voids and logarithmic spiral shapes in the filaments.
Okay, those are huge scales. What about lab tests? Tabletop experiments that could prove or disprove this decisively.
These are crucial because they're more controlled. Prediction B1, Casimir symmetry correction. The Casimir effect is a real quantum force arising from vacuum fluctuations. The claim, the shape of a tiny cavity, its perimeter symmetry, should affect this force, even if the area and gap are identical.
So a hexagonal cavity would have a slightly different Casimir force than a square or decagonal one of the same size.
Exactly. You'd need incredibly precise microfabricated cavities, cooled way down, isolated from vibrations. Measure the force very carefully. If there's a consistent symmetry-dependent difference beyond standard predictions,
That's huge. Geometry affecting the quantum vacuum.
it would be revolutionary. Then there's B2, boundary-coded interference. Think of the classic double-slit experiment with light or electrons.
Okay.
The claim, if you impose phase patterns like 13 versus 15, using electrodes or masks around the slits, you can shift the resulting interference pattern on the screen, even if the total number of photons and their energy remains exactly the same.
So the boundary conditions phase influences the quantum outcome.
Precisely. You measure the pattern shift carefully. If it happens reproducibly, tied to the imposed phase symmetry, it's direct evidence of geometry steering quantum events. Again, absolutely fundamental if true.
Wow. Okay, moving into engineering applications. Materials, energy, even water.
Yes. Prediction C1, metasurface energy rectification. Claim. Thin films patterned with spiral designs could harvest ambient energy, like heat or electromagnetic noise, more efficiently than films with standard hexagonal patterns, even using the same material. Test it by making the films and measuring the tiny DC current they generate from noise.
Could lead to new energy harvesting tech. And C2, colloid self-assembly.
Right, we talked about colloids organizing, claim C2. At the same field strength, you can toggle how colloids self-assemble, switching them from hexagonal crystals to decagonal quasicrystals just by changing the phase coding, 13 versus 15 of the driving field. You'd measure the structure using X-rays or light scattering. Phase becomes a switch for material structure.
And water. You mentioned tuning water. D1.
Coherence lifetime in water. Claim. The quantum coherence of water molecules, how long they stay in sync, could be measurably longer when gently driven by phase patterns compared to simple rational fractions or random noise. Test using techniques like Raman spectroscopy or dielectric relaxation measurements. It suggests we could influence water's properties with phase fields.
This is all fascinating, but the biological and medical predictions feel like the most immediate, potentially life-changing ones.
They carry the most weight, ethically and practically. Prediction E1, phase-coded morphogenesis in living monolayers. This is the big one we discussed.
The cell sheet experiment.
Exactly. Claim. Phase alone selects outcome at equal power. 12 polarity, 13 hexagonal order, 15 spiral outgrowth. Test it, measure morphology rigorously. If phase toggles biological form, it changes everything in developmental biology and tissue engineering.
And E2, tumor normalization. This sounds almost too good to be true.
It needs rigorous testing, of course. Claim. Tumors might be in chaotic off-fraction phase states. Applying a gentle, corrective 13 closure field could potentially restore normal order and suppress malignant behavior without killing cells. Tested on 3D tumor organoids, measure organization, communication, invasion. If the 13 field normalizes them, it's a paradigm shift for oncology.
What about regeneration? E3.
Regeneration bias in planaria. Planaria worms are famous for regenerating. Claim. Applying phase-coded microcurrents during regeneration could steer the outcome. A 12 program might influence head-tail formation. A 15 program might increase errors or spiral forms. Constant power, just changing phase. Test by measuring regeneration outcomes.
And some of these you said are findable now, things people could look for in existing data.
Yes. The CMB residue, A1. Someone with the right skills could analyze public Planck data right now. The cosmic web bias, A2, analyze public galaxy survey data. Even the leaf morphology, related to E1, detailed time-lapse imaging of plant growth, correlating bioelectric fields, using dyes, with shape changes. These don't necessarily require building new billion-dollar machines.
Okay, so how do we judge success or failure? What's the decisive rule?
We need clear, pre-registered criteria, strict controls, especially keeping energy constant. Then, honestly assess if phase-only changes produce the predicted geometric outcomes.
What would count as a pass?
Let's set a high bar. Pass any two of those core lab tests, Casimir, interference, colloid monolayer with strong statistical significance and independent replication. And find convincing evidence for one of the sky-level signatures, CMB or cosmic web.
And if it fails these tests?
Then the theory, as stated, is wrong. We revise it drastically or we retire it. That's science.
But if it passes?
Yeah. If it passes, we're not just looking at a new theory. We're looking at a new toolkit. a fundamental understanding of how geometry emerges from time with the potential to perceive, predict, and maybe even shape reality in ways we previously couldn't even imagine. It moves from fascination to function.
Wow. Okay, let's try and wrap our heads around this. We've gone incredibly deep today into this time fraction spiral law. We've explored how the universe, from the tiniest scales to the absolutely vast, seems to organize itself not randomly, but through these phase relationships. When smooth systems get disturbed, they don't just dissolve into chaos.
They fracture, they fold into these specific time fractions, 12, 13, 15 primarily. And these fractions aren't just numbers, they lock into fundamental geometries. Polarity from 12, stable hexagonal closure from 13, and the dynamic, ever-present spiral from 15.
And the spiral. It really does seem to be the dominant theme, doesn't it? The universe's go-to solution.
It appears as this universal attractor of disturbance, of growth, of flow. It's the elegant answer to that geometric misfit inherent in the 15 fraction. You see it etched into your DNA, in the folds of your mitochondria, in the patterns of flowers, the arms of galaxies, the heart of storms. It's everywhere.
And crucially, this isn't just a beautiful idea to admire. It's a concrete, testable, scientific framework. It makes specific, falsifiable predictions we can check right now in labs and observatories.
That's the critical difference. The potential applications are staggering new materials, regenerative medicine, maybe even new ways to think about energy or the fundamental forces. If we can truly understand and harness this.
It changes the game entirely. So the provocative thought to leave everyone with, what will you look at differently now? Knowing that under the surface complexity, these profound geometric laws, driven by simple relationships in time, by phase, might be constantly shaping our world.
The universe is speaking a language of shapes, a language of geometry emerging from time. We're only just beginning to tune in, to learn how to listen, and perhaps how to speak back.